Welcome again to Engineering Science 211, Materials Safety and Equipment Overview for Nanotechnology. We're in Unit 2, and we're talking about infrastructure. And infrastructure deals with the facilities used in nanotechnology and the equipment used in nanotechnology. And so we have talked about infrastructure, and as we see, we've asked the question, what is it? Why do we need it? We've talked about facilities, and now we're talking about equipment systems. Last lecture, we talked about vacuum-based systems, and we saw how they were very important, very widely used in processing and in characterization. In this lecture, lecture 4, we're going to stop for a minute and look more closely at vacuum systems. In fact, we're going to look at vacuum systems in this lecture 4, in lecture 5, and in lecture 6. Vacuum systems are so important, we need to make sure we understand what they are and the terminology that is used. So for these next 3 lectures, including today, we're going to talk about an overview of vacuum systems, the basics of vacuum, mass flow controllers, vacuum gauges and valves, and vacuum pumps and leaks. So today is lecture 4, part 1. And the outline for today's lecture is overview of vacuum systems, basics of vacuum, and mass flow controllers. And we're going to begin the lecture by discussing an overview of vacuum systems and some of the basics of vacuum science and technology. Well, vacuum-based systems. Why do so many types of equipment use such systems? Why go to all the trouble of creating a vacuum? Well, you do that because these vacuum chambers are very useful for controlling contamination and in processing for controlling the process itself. So, given this tremendous importance of vacuum systems, it's very crucial to us that we understand vacuum science and technology. So, again, why is vacuum so important? Well, a simple way of putting it is vacuum equals clean. If there's nothing there, it should be clean. And in vacuum, we pump everything out, so there should be nothing there. It should be very clean. So vacuum-based processes are common in nanofabrication because they offer a reduction in ambient contamination. The conditions that they establish are very repeatable, and vacuum is necessary for high aspect ratio plasma processing. In other words, vacuum is necessary for things like anisotropic etch and profile control, the things we talked about in lecture 3. Vacuum means that we've created a volume where we have removed gas molecules, the gas molecules that normally would be present. Air molecules, oxygen, nitrogen, for example, moisture, water vapor, and any gas residues that might be present in the environment, they're all removed in some defined container. We generally call it a vacuum chamber, and we have achieved a pressure in that vacuum chamber that is less than that found in the atmosphere. If we didn't do this, there's many processes in modern nanofabrication that we just could not carry out. Vacuum-based processing in a chamber is very important to control processes, to control contamination, but as we have also seen, it's very important for many characterization techniques. Now, we're going to talk about taking a chamber and establishing a vacuum inside here. There's another use of vacuum systems that I just want to mention, and that deals with taking a block and putting holes in it, and then having that off to a vacuum pump, and then putting your substrate, and then establishing a vacuum under here to hold the substrate down. This is a simple use of vacuum as a substrate holder. So we're just going to accept this. This is an everyday use of vacuum as a substrate holder. We're very interested in this, the use of vacuum to define a volume which is very carefully being established in terms of the contamination, what's in that volume, the pressure in that volume, so on and so forth. This is the kind of vacuum systems we're interested in. So vacuum conditions. Vacuums create clean environments. They create low molecular density. They increase the mean free path. And a clean environment means that they remove particles, unwanted gases, moisture, and contaminants. Well, that's very good if you're going to have any kind of yield, if you're going to have any kind of process control. Sometimes you have gases that are dangerous. You want those in a very, very well-defined, clean environment. Low molecular density. By reducing the pressure, we have fewer molecules and atoms. If we have fewer molecules and atoms, and then we obviously reduce contamination, and we reduce the possibility that those molecules and atoms can get involved in our processing. We don't want them there. We don't want them uncontrollably involved. And if we reduce the molecular density, then obviously there's fewer molecules, and if something like an electron, for example, or an ion, or a radical is traveling, then it has a much less of a chance of undergoing a collision and being diverted. We don't want that to happen. We want to know where they're going. So by having low pressure, we reduce the chances of these collisions, and we increase the mean free path, the distance between collisions. So mean free path control is very necessary for creating plasmas and for affecting the energy of the plasma and for affecting the directionality of beams and for controlling etch profiles and so on and so forth. Mean free path is very important also, and it can be controlled in vacuum systems. So vacuum systems are typically assessed in terms of the pressure, which is measured in torr. Atmospheric pressure is 760 torr. So generally speaking, to keep it in my mind, simply I think of atmospheric pressure as being 10 to the 3 torr. I like to use TORR as the abbreviation for torr because I always confuse T with temperature. So I like to write out TOR for torr. So atmospheric pressure is about 10 to the 3 torr. Okay, it's really 760, but I remember it as 10 to the 3. Generally speaking, when you then lower the pressure below this, you're creating a vacuum. And there's 3 vacuum ranges that people talk about. There's low vacuum, that is, it's not a very good vacuum. It's also called a rough vacuum. Then there's high vacuum. This is pretty good. So this number 10 to the 3 has really gone down. Here it's gone down. Here it's really gone down. And then there's ultra high vacuum. This number has really gone down. So we've removed molecules, so the pressure goes down. Rough vacuum or low vacuum, high vacuum, ultra high vacuum. So here's some numbers to associate with these vacuum ranges. We said rough vacuum or low vacuum, high vacuum, ultra high vacuum. Here's some numbers to associate with that. Rough vacuum is atmospheric pressure, which is 10 to the 3 torr, down to 10 to the minus 3 torr. That's considered rough vacuum. High vacuum is 10 to the minus 6 torr to 10 to the minus 3 torr. So this range is high vacuum. So let me write it in the same direction, that is high, low pressure. So it's 10 to the minus 3 torr, the end of this regime, down to 10 to the minus 6 torr. So we're getting lower. It says high, but the numbers are getting lower. And then ultra-high vacuum is pressures that are 10 to the minus 6 toward the end of this regime and lower. So these are high vacuum, or ultra-high vacuum pressures. Now, the things that happen when you look at these different pressures can be seen here. So here's pressure in torr. So atmospheric pressure is up here, and a low vacuum is in here, high vacuum is in here, and ultra high vacuum is down here, just to see where things are happening. So this is a very, very interesting set of information. This shows you the density of the molecules and atoms that are present. And the density is given in per cubic centimeter. And you can see that we have very high molecular densities here. And then as you reduce the pressure, the density of molecules present in the chamber decreases until very, very low values, very, very low densities of molecules. The mean free path can be seen over here. This is given in centimeters, and this is given in time between collisions over here. But you can see the mean free path in the atmosphere, in the room I'm in, the room that you're in. The mean free path is extremely small. This is about 10 to the minus 6 centimeters. 10 to the minus 6 centimeters is a very small distance, obviously, and that's the mean free path. Now, if you take the pressure and look at it, say in this part of the, lower the pressure down to this part of the high vacuum region, you can see the mean free path has gone up to being a centimeter. If you go into this part of the ultra high vacuum, let's say 10 to the minus 8, then you can see the mean free path has become 10 to the 6 centimeters. Wow. Big difference. And of course these are the times between collisions. So as you lower the pressure, many less molecules, therefore longer distances between collisions, therefore longer times between collisions. And you can see that on this data. Over here, monolayer formation, this is interesting. In other words, if you have a substrate sitting out, and if you go down here to ultra high vacuum, see that a monolayer of contamination forms in something like maybe 8 minutes. By the way, what's a monolayer? A monolayer means, mono is one, and it means one layer of molecules or atoms sitting on the surface. If you pump down to say 10 to the minus 12 torr, and then you can see it takes a week to form a monolayer. This gives you some idea of how fast surfaces get contaminated. Real appreciation for what's going on inside a vacuum as the molecules are all running around. Even at these very low pressures, with these very low molecular concentrations, and these very long mean free paths, still molecules and atoms are coming to the surface. Some are sticking, and eventually you can form a monolayer of contamination. So to understand vacuum systems, vacuum technology, vacuum science, we need to understand gases, because it's the gases we're pumping down, it's the gases whose molecules we're trying to control in their number, in their density. And basically a vacuum is used to control these gases or remove gases. That means that we need to think a little bit about gases. So some properties of gases are tabulated here. Gases of equal volume and pressure have the same number of molecules. So if you keep the volume constant and pressure constant, or if you have gases of equal volume and equal pressure, here's one gas, here's the other. Keep the pressure the same, keep the volume the same. Then you have the same number of molecules here. Oops, I should make this a little bigger. And the same number of molecules here. Gases are compressible, we all know about that. Gases expand with increased temperature, we know that. Gases mix completely. The total pressure of a mixed gas, a mixture of gases, is the sum of the pressures of each. The pressure, if you have constituent A and constituent B, the pressure of this plus the pressure of this is the total pressure. You'll call the pressure of constituent A the partial pressure of A. You'll call the pressure of B the partial pressure of B. And gases fill a container completely, regardless of the pressure and shape of the container. Gases, of course, are made up of tiny particles, molecules and atoms, and we know they're constantly moving around and suffering collisions, banging another one going around, and that's what's happening inside a gas. And their speed is influenced by temperature. The speed, V, is proportional to temperature to the 1/2 power. Now pressure, so temperature is a measure of the motion running all around, the speed. Pressure is a measure of the force exerted on a unit area. And the force is generated from gas particle collisions. And a system under vacuum has a portion of these particles removed. Obviously, some of the molecules have been taken out. This reduces collisions, as we saw. It increases time between collisions. As we saw, it increases the mean free path, as we saw. And reduced collisions means reduced pressure. A couple more comments about pressure. Pressure is the force exerted on an area. So when an atom of a gas collides with a wall, it rebounds with its velocity and momentum in a different direction. That causes a force on the wall. That happens because of Newton's laws. The total momentum must be conserved. So momentum is transferred to the wall. That is, the wall feels a force, and that's what we call pressure. So if you have a wall, gas molecules are running all around. Some hit the wall, they bounce off. The change in momentum causes a force on the wall. That's what we call a pressure. Maybe this isn't a wall, maybe it's a pressure monitor. And it feels the pressure because it feels the momentum change here due to the molecules bouncing off the wall. That's pressure. So here comes the molecule in, hits the wall, bam, and that creates a pressure. And of course, there's lots of molecules doing this constantly. So the momentum P of an atom just before, or a molecule just before striking the wall, must be equal to the vector sum of the momentum of the rebounding atom plus the momentum of the wall. So this is Newton's laws. Momentum is conserved, and so the momentum afterwards, this particle is going this way, its momentum is in this direction, so now the wall has a little bit of momentum in that direction. It's felt a force. It's this plus this has to equal that. That's felt a force. That's the pressure. And the constant bombardment on the wall, it's happening so many times per second that the wall essentially feels a steady force. Well, lots of ways of measuring pressure. The most common was developed 400 years ago, over 400 years ago, and it's the mercury barometer, and it operates by balancing the weight of a fluid of known weight, like mercury, against the weight of air. And it was invented by Torricelli, and of course that's why the unit for pressure is torr, in his honor. So the mercury, if you have a column of mercury in a piece of glass, it has a certain weight, and then balance it with the force from the atmosphere, and that's how we can basically measure pressure. Here's a better drawing, and so you see there's a vacuum up here, so there's no force up here at all. So the only force you have is the weight of the mercury, and the only force you have countering it from flowing all the way out is the atmospheric pressure here. So we can then, with this height, we can measure the pressure being exerted by the atmosphere above the Earth. So the average pressure of the Earth's atmosphere at sea level is 760 millimeters of mercury, which is 760 torr, which, as you remember, I kind of remembers 10 to the 3 torr. This is not right, that's right, but I sort of remember it's about that size. So that's a simple way of measuring pressure with the mercury barometer. Now, of course, we don't like to use mercury barometers anymore because mercury, as we know, is a dangerous heavy metal. So we don't like to use that type of way of measuring pressure. Our atmosphere has all kinds of gases in it. The standard composition at sea level is about 78% nitrogen, 21% oxygen, argon about 1%, and then carbon dioxide, neon, helium, krypton, hydrogen, and xenon. These are the things that are found commonly in our atmosphere. Unfortunately, also found in our atmosphere are things like carbon monoxide and some other man-made chemicals that, man-made gases that can cause pollution problems. But here is what should be in a standard natural atmospheric situation. So the types of gases are listed here: nitrogen, oxygen, argon, carbon dioxide, neon, helium, krypton, hydrogen, xenon, and water. And you see that the symbols, which you're familiar with from chemistry, here are the percentages that we just talked about. We know on a humid day this can be pretty high, and this is the partial pressure these are partial pressures, we talked about those. This is the partial pressure here's the partial pressure for water vapor, and of course this would be a humid day. So the air around us exerts onto the Earth's surface a pressure of 760 torr, which in English units is 14.7 pounds per square inch. This is the weight of the air pushing on the Earth's surface, and we call it atmospheric pressure. Of course, we know this varies a little bit with the weather. We talk about high pressure, low pressure systems moving in, but this is an average pressure at sea level. Now, mean free path, we've talked about that. That's how far a gas or molecule travels, a gas atom or a gas molecule travels before it strikes another gas molecule or atom. And when the pressure is lowered, the space between the gas molecules increases and the mean free path gets longer. This is important for processing. It's important because of plasmas, for conformality, edge profile, reasons that we've mentioned earlier. Mean free path, well, you want to get the mean free path to be very long because that means you've gotten rid of the gas, which you want to do for process control and contamination. But by getting it very long also, you have this impact on plasma generation, conformality, and edge profile. So the mean free path, affectionately known as MFP, varies according to vacuum range. The lower the vacuum, the longer the mean free path. We saw that quantitatively a few slides ago with that data. Here's more information on to stress again the importance of pressure. Here's atmospheric pressure. This is low range of the rough vacuum or low vacuum, and this is into the ultra high vacuum range. So three different regimes: atmospheric, just the edge, just the lower pressure edge of rough vacuum or low vacuum, and here into the ultra-high vacuum range. The number of molecules per cubic centimeter, this number 10 to the 19 is a good number to remember. That's number per cubic centimeter. If you lower the pressure down, then this is lower the pressure by what? It was 10, you see, this is why I like to use 10 to the 3. It's easy for me to look at. It goes from 10 to the 3, that's atmospheric, to 10 to the minus 3. So you've reduced the pressure by 1,000,000 times. And if you do that, then the number of molecules is down, per cubic centimeters down to that number, 10 to the 13. And if you reduce it down further, down to 10 to the minus 9 torr, then the number of molecules per cubic centimeter is 10 to the 7. The mean free path atmospheric pressure is 10 to the minus 6 centimeters. We mentioned that earlier. At 10 to the minus 3 torr, it's 5 centimeters. So it's gotten a lot bigger, from 10 to the minus 6 centimeters to 5 centimeters. And now the mean free path, if you go into the ultra-high region, and it's 10 to the minus 3 part of the ultra-high region, 48 kilometers is the mean free path. So mean free path and molecular density are obviously very, very related. And the table that we just looked at shows us what we need to do if we want to control the mean free path, the kinds of pressures that we need, the pressure ranges. And remember, the mean free path is important because it controls conformality, etching, plasma generation, but it's also important because it's another way of measuring how many gas molecules are around and what kind of contamination might be present. As you can see, the mean free path can also establish the size of a process tool because it controls the distance over which the molecules or the atoms get suffer collisions and bounce all around. The mean free path distance is also critical to understanding plasmas that we mentioned, and in general, vacuum is very, very important, and we need to understand it, and we need to understand it for material processing and system design. Gas flow. Well, if we've created a vacuum in here, it doesn't do us any good unless we can do something. So we have to put a sample in here that we're going to do something with. So we're going to need some kind of an antechamber here, or a load lock chamber that we can pass a sample into. We've discussed those before. So there has to be some way of pumping this down, creating a vacuum. Well, putting the sample in, pumping it down, creating a vacuum, and then passing it into the pristine processing chamber, and then taking it back out when the process is over. But lots of times in our discussions, we don't bother showing the antechamber or the load lock chamber because we know it should be there in a really well-controlled processing situation. But we often have to put gases in because maybe we're going to try to create a plasma to use for etching, or a plasma to use for deposition. Maybe we're not going to use a plasma at all. Maybe we want the gas to come in and we're going to decompose the gas using a laser beam. Or maybe we're going to decompose the gas just using temperature, and we're going to have the gas react in the positive film. In any case, we can see that in many situations we need a gas coming in, and of course then we need a way to get the gas out. We need pumping systems, and we need filters, and we need ways of getting the gas in. So we can see that there's going to be lots of situations where gases are going to be flowing inside these processing chambers, which are vacuum chambers. Now, when the gas flows, there's two regimes. It can be the viscous regime or the molecular regime. And that distinction is important because it affects the way we design this process chamber. Because we want to think of the way these molecules arrive and how they move around in here. So we want to think about their flow, and we need to think about whether it's viscous flow or molecular flow. Okay, what do we mean by that? Well, viscous flow means that we've got enough molecules around that the interaction among the molecules is important. The viscous forces between the molecules, which is kind of a, viscous force is a fancy way of trying to account for the collisions that the molecules suffer on the sides from other molecules. We call that viscosity. But really what's going on, what's really causing viscosity is the collisions going on, interaction among the molecules. And so that's viscous flow, where these interactions are very, very important. Molecular flow is when there's very few molecules, and generally there isn't any interaction at all among the molecules, unless they would happen to collide. And then, of course, there'd be an interaction. But generally speaking, molecular flow, the W here needs to be put on there. In molecular flow, there are very few interactions among the molecules. So viscous flow, the molecules are closely packed together and are constantly bumping into one another. The molecules are so closely packed together that as a vacuum pump removes some of them, others rush in to fill in the empty space immediately. So there's a real flow situation going on there. Viscous flow conditions allow the movement of great quantities of molecules per unit time, because it's a real flow situation, like water flowing in a stream. It's a viscous flow situation. Molecular flow, that's when gas molecules have been removed from a chamber, or most of them have been removed, and the molecules are so far apart that they no longer have any influence on each other. Statistically, a gas molecule might travel inches, feet, or miles. You know, that depends on the mean free path, before it collides with another gas molecule, and of course, as we just said, depends upon the vacuum level. Here is a diagram that shows us the transition between viscous flow and molecular flow as a function of pressure. So at these higher pressures, you'd expect viscous flow at these higher pressures, and you get it. If you go to the lower pressures, you'd expect molecular flow, and you get it. There's a transition, and the transition from one to the other also depends on the system dimensions. And the reason for that is that molecules can undergo collisions, but if the mean free path is long enough, the collision they'll undergo is with the walls of the processing chamber. So the processing chamber size comes in also in determining the type of flow. So you have the system, the tool, the vacuum chamber size, the pressure that determines whether you're in the viscous range of flow or the molecular range of flow. So we've talked about an overview of vacuum systems. We have talked about the basis of vacuum, the basics of vacuum. So we understand how the molecules running around, the random nature of the molecule motion. We understand that how pressure is created. We know the role temperature plays. Let's talk about the situation now where, as we said, we've created a vacuum. We have a vacuum inside here. We want to do some processing. So we want to introduce some gases. And we want to use those gases to create a plasma, or we want to use to do etching or deposition, or we want to use those gases to interact with a laser beam, so there's some chemical reaction producing deposition on a substrate, or we want to use temperature to interact with that gas to produce a film on a substrate, and then of course we have to pump the fluid back out. So we're very interested in gases, or the lack thereof is a vacuum, but once we get the vacuum, we want to reintroduce the gases on our own terms very often. We want to introduce the gases in a very controllable way. We talked about evaporators in lecture 3. Generally speaking, we don't want to introduce a gas unless we're going to evaporate something. I think we mentioned evaporating titanium, for example, as an example, and we wanted to form titanium oxide. then we'd want to evaporate the titanium and introduce oxygen in. So even in simple physical vapor deposition situations in a vacuum system, we may be interested in gas flow. So gas flow is often encountered in vacuum systems. So we have the flow of the gas in, we want to control that. Then we have the flow of the gases out, and we want to control that. So that means that we often need to use mass flow controllers, MFCs. So we want mass flow controllers because often we want to controllably introduce gases into a vacuum chamber. Mass flow controllers control the flow of a gas into the vacuum system. For small systems, they are rated at 1 to 100 SCCMs. SCCM stands for standard cubic centimeters per minute. So that's a very typical unit that's used to measure gas flow. Larger systems need maybe standard liters per minute. Standard liters per minute. So they may be calibrated in that set of units. Mass flow controllers that use heat transfer to measure the flow are calibrated for the specific heat capacity of a gas. The default calibration gas is nitrogen, and then there's usually an adjustment to correct between nitrogen and the gas in question. So this type of mass flow controller uses some kind of an element that's heated, and the gas flows by, takes heat from the heated element, thereby cooling it, and then you monitor how much power it takes to keep this at a fixed temperature, so you know how much heat's being taken away, therefore you know the mass flow. However, gases have different specific heats, different abilities to carry heat. And so the gas comes by, it takes the heat away from this heated element. The heated element temperature would change if you didn't put more power in. You put more power in, therefore you know what the speed of the gas is. But that's assuming the specific heat capacity of the gas. If the gas used is usually nitrogen. If it isn't nitrogen, you have to account for the heat capacity of the gas that you do happen to have flowing in. And often there won't be nitrogen because we're trying to make a plasma, or we're trying to use oxygen to react with something, or many, many different varieties of gas. Therefore, many, many different varieties of gases are used. Here is a depiction of some mass flow controller system or tools or instruments. This is a simple type that uses a ball, and the gas comes in. You turn this, and depending on the speed of the gas past the ball, it can hold the ball at different spots here. Faster, the more it can push the ball up. This is calibrated so that you can know the mass flow. And for example, this one is calibrated in standard liters per minute, using air as a calibration gas. So this type of mass flow controller is called a rotometer. Here's another type that uses a pressure sensor. So depending on the speed of the gas, the pressure sensor gets different readings, and then with the pressure sensor calibrated, on measuring pressure, the circuitry can then convert that pressure into speed of the gas. So this type uses pressure, and the calibration, of course, involves knowing how the mass flow is proportional to the pressure picked up by the sensor. So that's developed by the tool vendor, the tool producer. Here is the thermal mass flow control type that we're talking about. There's an element here that is heated. Generally, power is delivered to keep the temperature of this element the same. Depending on the gas going by here at its speed, you have to supply more power or less power, and thereby you know the speed of the gas. As we said, you have to know the specific heat of the gas specific heats are measures of how well the gas takes away heat. And generally, these things are calibrated for nitrogen, assuming the gas is nitrogen, and then there are correction tables if you have other gases. So these are 3 examples of mass flow controller. So it's important to define the chamber with the vacuum. You create a base pressure, that is, you pump down to a certain pressure in the high vacuum range generally, maybe the ultra-high vacuum range, very well-defined environment, and then you introduce gases and you control that introduction with these mass flow controller type of instruments. So to summarize this lecture on vacuum part 1, we have overviewed vacuum systems by discussing why they're so useful. We have gone over basics of vacuum science and technology, and we have introduced the instrumentation that's used to control the flow of gases into and out of vacuum systems.